Okay, hello and welcome to week two. So we continue off where we stopped with phases of matter. So today we'll be discussing how matter changes phase. So the four primary states of matter: solid, liquid, gas, and plasma. So here we can get this. You can get matter in case of fluid materials that we'll be dealing with in this module. You can get it to move from phases by adding heat to them, okay? Uh, Especially from moving from solid to gas. In the case of plasma, there are other ways to get matter to convert to plasma that is not just by adding heat, okay? And that will form a different explanation and for another module. But in this case, we are concerned with what are the actions that we do that we can do to move matter from different phases. And this is also reversible state, okay? From solid to gas and gas to solid, they are all reversible. And some of you who have done the ITF previously will already been exposed to this. So starting from the first one, the solid. So what are the characteristics of a solid? Solid, they have a fixed shape and size, and this is due to the intermolecular forces holding the atoms and the molecules of the solid. So the forces, these intermolecular forces are very strong, and because of their the strong bond between them, they have this rigid form. Now the molecules itself, they vibrate, but they are only vibrating around their equilibrium position. So they are like string, they are like attached to strings, but they don't freely move away from their equilibrium position. So they can vibrate or oscillate just a tiny bit around the equilibrium state. Okay, so this gives the solid the fixed shape and size as well. So if the molecules cannot move relative to each other but continually oscillate about their equilibrium position, at a sufficient temperature, the velocity of the molecules may reach a point where the intermolecular forces are partially overcome and the groups of molecules break away, and this leads to melting of solid. So this is when temperature is increased. Okay, in the case of heating a solid ice cube, if you add temperature to it, these intermolecular forces holding the atoms together becomes weakened, and thereby the ice block starts to melt, and this triggers a change in phase. Now, for the liquids, so if a substance is heated, a solid substance is heated, and the molecules have more energy, the molecules no longer reside a fixed position relative to each other, and they can rotate and translate freely. So the intermolecular forces are now so weak that they cannot maintain the shape, they cannot maintain a fixed shape or structure. Then the atoms can move freely. Um, the major difference between the solid and the liquid is that the actual molecules can actually move freely, and because of that, it gives the liquid its property. So the properties of the liquid, as we know it, is that the liquid, although it doesn't have a fixed shape, but it has a fixed volume. Why so? If you put a liquid in a cup, like as you can see in this diagram, now although the intermolecular forces holding the atoms of this liquid is weaker than that of solid, but it's still strong enough that the atoms are still held together within a particular area, and because the atoms, the bond itself are not giving the atoms a rigid position, then they can easily take the shape of any container where they are put in. So if you put liquid in a cylindrical container or rectangular, whatever shape of container you put it in, this molecule will flow easily to take the shape of its container. But it has a fixed volume. The fixed volume is already shown here. So if you pour water halfway the cup, then there will be a definite height of water in that container. So if you have a 5 meter high container and you pour water up to a 2 meter level, then that would be the specific volume or the fixed volume of that particular liquid. And that is as a result of the nature of the connecting intermolecular forces of this acting in the liquid, okay, with the atoms in the liquid. Now, if the substance is heated further from the liquid phase, then the molecule becomes even more energetic, and the molecules become, the movement of the molecules becomes more random. Then the intermolecular forces are very, very weak, more or less non-existent. Then these atoms can move freely, colliding into each other and moving as far away as possible from each other, and also as close as and bouncing off each other. So what happens? Because of this, the atoms itself loses their density, and when they lose their density, they cannot have any fixed shape or volume. So that means we can easily expand or compress these particular atoms now. But what happens is when you put these atoms, or in this case gas, in any container, it will fill up any available space within the container. So the difference between a liquid being poured in a cup and the difference between a gas being poured in a cup. Now, the gas will escape from the cup because the cup is an open system. So the reason the gas will escape the cup is that there is more space within the room where the cup is. So the gas will tend to fill up the whole room rather than just the cup. But the liquid will take the shape of the container and will only have, we have a specific volume, and that is due to the intermolecular forces holding the molecules and the atoms together compared to that of gases. The gas does not have any intermolecular forces holding the atoms together, so the atoms are free to move wherever they can. They can take up any space they want. Okay, but another quality that this or the characteristics that the gas brings is that it is easier to compress and expand this gas. So to change a pure substance from a solid to liquid, uh, we do perform what we call melting, and that is done by adding heat to the system. And also to boil liquid into gas, then we convert liquid to gas. A process is called boiling, and we need to supply energy in form of heat in order to achieve this. Now, to reverse the process by condensing gases or changing the gas from gas phase to liquid phase, we need to condense the gas, and by doing so, we are extracting heat from the system. Similarly, if you want to freeze liquid to get them to solid phase, then we need to also extract the heat out of the liquid phase in order to achieve this. Okay, so here you can see the boiling, for the boiling, which is the from melting of solid water, which is ice, melting it to liquid and boiling it off, vaporizing it to gas phase. We need a boiling system. Then to get it back to solid, we need a refrigeration system. So in the boiling system, we add heat. In the refrigeration system, we remove heat. Okay. What we are trying to what I'm trying to explain here is that the total amount of energy required in form of heat to vaporize a solid water, a solid ice, will equal the amount of the total energy that is removed from the gas in order to get it back to a solid. So there are many practical situations where two phases of pure substance coexist in equilibrium. Typical example, water, liquid vapor existing during a boiling process, or during a condenser and in the condenser of a steam power plant. So we will focus on liquid vapor and liquid vapor mixture phases. As a familiar substance, water will be used to demonstrate the basic principles involved. However, all pure substances exhibit same general behavior. So let's take, for example, a compressed liquid at a pressure 1 atm and temperature of 20 degrees Celsius. So if under these conditions, the content of this tank here, okay, this is a cylinder, a cylindrical tank with a piston. Okay, the gray bar here is the piston. Under this condition, that's the temperature condition. The water is exists as a liquid. Okay, and a a compressed liquid is referred to as a liquid that is not about to vaporize. Okay, so when we say compressed, it means that the pressure is manipulated to remain at a constant pressure. Okay, there is some work, some sort of work done to the pressure, done to keep the pressure where it is. Okay, that's what we mean by compressed. Okay, so what happens when heat is added to a compressed liquid? So the water will remain as a liquid state and the water temperature will increase. The specific volume will slightly increase. That is, there will be a slightly movement, but very, very small movement of the piston here. Uh, and the pressure will remain constant. Now, we refer it as constant pressure because we are doing work to maintain the pressure constant, okay? Now, this process will remain, all this will remain the same until the temperature of the system increases up to 100 degrees Celsius. Now, when that happens, uh, any heat added to this system will start to vaporize the liquid water. Now, what will happen is that the phase change from liquid will happen on a gradual process. And this is at the point where we say that we have reached a saturated liquid because a saturated liquid is a liquid that is about to vaporize. Now, you can see this, or I don't know if any of you have noticed this. When you are boiling water in a kettle, the initial thing that will happen is that obviously nothing will happen. Then all of a sudden, there are some development of tiny bubbles at the bottom of the kettle. Then these bubbles will continually rise. Then at this stage of saturated liquid, this is when there are tiny formation of these bubbles almost rising up to the surface of the water. So at this stage, this is a liquid that is referred to saturated because the liquid is about to vaporize and the temperature is at 100 degrees Celsius and the pressure corresponding to this temperature is 1 atm. So um, the next phase that happens after the saturated liquid is the saturated liquid vapor mixture. So at this stage, once the temperature stop rising, so at this point we can say that the system has reached a kind of a thermal equilibrium because the pressure remains at 1 atm and the heat is continually added to the system, but the temperature stops rising. Now, when the temperature remains constant at 100 degrees C, pressure remains constant, then what happens? Uh, the changes in the system, okay, will be a large increase in the volume and a steady decline in the liquid level. So what is happening here is that some amount of the liquid water, which is denoted in the color pink here, will evaporate, okay, and the volume of the system, the piston, increases. Then the vapor phase is formed now, but the quality of the vapor here is still low because that vapor is a saturated vapor because some of the vapor will condense back to the liquid phase, but as it condenses back to the liquid phase, then you have a saturated liquid as well, which will also evaporate to a vapor phase. So this system, due to the maintenance, due to there is no a change in the temperature and the pressure, then the equilibrium system will persist until a little bit of time given to the heat addition then the phase will change as well. So when we get to this stage, what are the characteristics of this stage? So this stage is where the liquid and vapor coexist together. So before the liquid completely evaporates, okay, so we refer to this as the midway, where, like I've already explained, as the midway point, where this line is. This is where there is exchange of vaporizing liquid from here and condensing vapor from here. So the gray bit here represents the saturated vapor, and the pink bit here represents the saturated liquid. So at this stage, there is constant exchange between vapor rising from the liquid and vapor condensing from the saturated side. Okay. So after the last drop of the liquid is vaporized, the entire cylinder is filled with vapor, and nothing else is no single liquid left within the system. Now this is the next step after the saturated liquid and vapor mixture state. Okay, when the heat is continually added and remaining at the same condition, the same temperature and pressure condition, then all the saturated liquid will be vaporized. Okay, and all we will have now is a saturated vapor. Now that saturated vapor is the opposite of saturated liquid, which is a vapor that is about to condense. So this is characterize what happens as we continue to add heat to the saturated vapor. Now, the temperature will start to rise, and as the temperature rises and the pressure remains constant, then the system is referred the what is left within the system, and also what we left within the system, the steam left in the system is referred to as superheated steam. Now, this is a high quality steam. This is a very dry steam. This steam is not the type of steam that is about to condense. This is a steam that will remain gas as long as the temperature increases above 300 degrees Celsius. Okay. Now, this system is characterized by high temperature, so increase in temperature, increase in specific volume, with the pressure remaining constant. Okay. So if we transfer some heat from the vapor and the temperature may drop somewhat, but no condensation will take place if the temperature remains above 100 degrees Celsius. Okay, so the superheated vapor is the vapor that is not about to condense. So this is the type of vapor, obviously, we need in any operation that involve a steam, that will involve a steam, the production of steam within the process. Because this is where you will get the maximum work from. You get it from the superheated steam. So we will get into that in the coming lectures, and we will see the application of this process in some of the systems that we've introduced in the introduction. Okay. Um, so how do we represent this process on a TV diagram or a PV diagram? So the constant pressure phase change could be of water in this case, could be explained using this TV diagram. So as you can see, at the initial stage, remember this is a constant pressure curve. So the pressure is constantly at 1 atm. So at 20 degrees Celsius and 1 atm pressure, we have the compressed liquid here. Now when we approach 100 degrees Celsius and 1 atm, then we get the boiling. This is where the saturated liquid started, where the vapor started to rise. Then between this point and point 3, and this is where the mixture of the saturated liquid and vapor existed. Now at this point 3, this is when all the liquid phase has been vaporized, and the only thing left is the saturated vapor. Now getting to point 4, okay, the temperature starts to rise at constant pressure, and that rise in temperature up to point 5, it identifies a system where the superheated saturated vapor becomes superheated vapor. So from point 4 to point 5, this is where we have a dry steam. Okay, and anything above that as well is referred to as saturated superheated vapor. So pairing it according to the initial descriptions we gave with boiling the cylinder and the piston. So at this stage, this is referred to as the stage one here. Okay. The second stage, stage two, which is here at the saturated liquid phase. Then stage three, which is already identified, this point here. So the point between these two and three, okay, that's referred to as stage three. Now at point four, this is the saturated vapor phase, and at point five, it is the superheated. But anything from point four to point five is referred to as superheated, and anything above, as long as the pressure remains constant. Okay. So if the entire process is reversed by cooling the water while maintaining the pressure at the same value, then the water will go back to state one, retracing the same path. The amount of heat released will exactly match the amount of heat added during the heating process. Okay, so it's a totally reversible process, and the energy added will equal the energy removed, as long as we keep the condition of the pressure and temperature, the condition of the pressure in this case, the same. Okay, if this were to be a PV diagram, then the temperature has to be kept constant. So it is probably it is not a surprise that water boils at 100 degrees C, but that is only correct when the pressure is at 1 atm. Okay, if there is difference in the pressure, then water will boil at a different temperature. So this is to say that there is what we refer to as a saturation pressure. So if you have a given pressure, then there is a corresponding saturation temperature, and that corresponding saturation temperature is the temperature at which water will boil. So giving an example, if a pressure inside a cylinder were raised, that same cylinder that we discussed in previous slide, were raised to 500 kilopascals, then by adding, we could achieve this by adding weight to the top of the piston, then the water will start to boil at 151.9 degrees Celsius. So as the pressure rises, then the boiling point will also rise. And the opposite will be for the opposite of this statement will also be true. Okay, so the at a given pressure, the temperature at which the pure substance changes phase is called the saturation temperature. So in this case, at 1 atm, which is equivalent to 101 kilopascals, the saturation temperature is 100 degrees Celsius. Okay. So the amount of energy absorbed or released during a phase change process is called latent heat. So latent heat is divided into, so for the amount of energy absorbed during melting, so the heat added to this system of solid to change it to liquid, and the heat added to liquid to change it to gas is referred to as the no the heat removed from the system when we want to compress it, condense the gas to liquid, and freeze the liquid to solid is referred to as the latent heat of fusion. Okay, so this is the heat removed from the system. But the heat added to the system in order to vaporize this solid to melt the solid to liquid and to vaporize this liquid to gas is referred to as the heat of vaporization. So the equivalent of that, which is the reverse form, is known as a condensation. Okay, so the magnitudes of latent heat depends on the temperature of pressure at which the phase change occurs. So this is simply trying to say that for us to determine what will happen, okay, we need to make sure that the temperature at which or the pressure at which the phase change happen determine the magnitude of this particular latent heat. Now, for the latent heat of fusion at 333.7 kilojoule per kilogram, that is only with respect to 1 atm pressure. So meaning that if the pressure of the water is different, then the latent heat of fusion is different. Okay, Similarly, this same statement is true for the heat of vaporization, and that is why we have a steam table that shows us these readings. Okay, but how did we determine the steam table and the properties table? Okay, so if that statement is true, that the magnitude of the latent heat is with respect to the temperature and pressure, then that means we can represent it on a curve. So during a phase change process, pressure and temperature are obviously dependent properties. And if we plot a saturation temperature versus saturation pressure curve for a liquid vapor saturation curve, then we will have something like this. So as you can see, as the temperature increases, as the pressure increases on the y-axis, so as the saturation temperature. So at 600 degrees Celsius, you can trace to find out where water will boil. Okay, so if you have a system that is compressed to a water that is kept at 600 kilopascals, then you expect that water to boil at a point closer or within 150 degrees Celsius. Okay, so what happens if we do the same, plot the same curve, the boiling curve on a TV diagram? Okay, so if we repeat the phase change process at different pressures, so if we have a different constant pressure, remember each boiling curve represents a particular constant pressure. Here, what happens? If heat is added to the system, and from this section, which categorizes the compressed liquid, you will see that the temperature at which the water boils, which is at this point, okay, increases as the pressure increases as well. Okay. Now, another thing to notice is that the the pressure, the pressure, the saturated liquid vapor pressure mixture region, which is the horizontal line here, diminishes as the pressure of the system increases. So if you are boiling liquid at a higher pressure, now the period where this saturated liquid and saturated vapor will exist in equilibrium will be reduced, okay, due to the increase in pressure, okay. So what happens? If this continues at a pressure of 22.02 megapascals, an equivalent temperature of 374.14 degrees Celsius, we reach a critical point. And that critical point corresponds to for this, we are talking about liquid water, correspond to a specific volume of 0.003155 meter cube per kilogram. Now, what happens at this point? As you can see, this point is a point where there is no difference in the saturated liquid and saturated vapor uh, mixture. Okay, they exist almost as the same. Now, but what is predominant? We have the condensed, compressed liquid line. Okay, from here, it seems that the compressed liquid line, once it gets to the temperature of 374 degrees Celsius and this pressure, it quickly becomes a superheated steam. Okay, so this point here identifies the point where the saturated liquid and the vapor mixture exist. So they are this point, because it's existing as a point and not a horizontal line, this point is where they are identical. So there is no big difference between the two of them. Okay. So why do we want to know about this critical point? Okay. So as we've already established, there are both the critical point is the superheated vapor, and below is the compressed liquid. Okay. So um, if we use that particular curve now to reproduce the TV diagram, then and we kind of use the highlight of the boiling curve, then we can now use this to visualize what the three major regions involved in this phase change of the liquid water will look like. And based off of this, we can use this to proceed in order to explain the systems that uses water or steam in this process. Okay, so by reproducing that diagram using the curve for the critical point, then we will have something that looks like this. Now, this line, from this line to this point, critical point, will now represent the compressed liquid region. So, and any point beyond the critical point will represent the superheated region. Now, in between this curve now is a point where the saturated liquid vapor region exists. Okay, and there is no much difference between this saturated liquid and vapor region. So, and tracing out the original boiling curve with respect to constant pressures, okay, we can see how water from here, compressed liquid, boils at this point, and saturated vapor evaporates completely as superheated vapor at this point. Okay, so the saturated liquid and saturated vapor lines meet at the critical point to form a dome, and as we already know, the different regions that make up the TV diagram at this point for boiling. Then, like we said, if we represent this diagram, if we represent it from the TV to a specific volume diagram, the only difference is that the temperature will now remain constant. But what happens, the compressed liquid will boil as the pressure reduces. So if as the pressure reduces, then at some point the water will boil, and when the pressure continues to rise at constant temperature, then we get a superheated steam. Okay, so the opposite of the TV uh, diagram. So this is the side-by-side view of the two. So on a TV diagram, pressure remains constant, and the temperature, the boiling point of compressed liquid is as a result of temperature rising due to heat added. And that temperature, the boiling temperature, is the saturation temperature, which is dependent on the saturation pressure in this case. Similarly, the same thing happens here as well. So the constant temperature will now determine the saturation pressure at which the compressed liquid will boil here. Okay, so as shown on the property table, steam table, this is an extract from steam table. You find out that at 1 degree Celsius, the saturation pressure is equivalent to 0.006566 bar. Okay, same as the saturation specific volume of the gas. Okay, the Vg here refers to steam. So other sections of the steam table gives us more information about the compressed liquid and the saturated water and saturated liquid and vapor phase, and also the superheated vapor. Okay, so there are in steam table, all of these are, I know some of you have already started using steam table, so you must have come across these tables and have actually used it for your calculations. So going further, we need to clarify and explain the different ways we need to identify the most subscripts used in the steam table in order to produce clarity of an understanding of how to use the steam table. So whenever you see a subscript F on the steam table, as you can see here, this point and that, then this denotes saturated liquid. Okay, if you see subscript G, which is that, you can see it here as well, you can see it there for entropy as well. This denotes the saturated vapor. Now when you see the subscript FG, then this shows the difference between the saturated vapor and liquid. So this is just a simple subtraction. So in the case of enthalpy, this enthalpy here obviously is referred to as the latent heat. Okay, but this value here is just the difference of subtracting the enthalpy of the gas. You subtract the enthalpy of the liquid from it, and you will get the latent enthalpy, okay? So the enthalpy in this case, latent heat, okay, required to get the liquid from this point to that, okay? So this is the difference of this, so Hg minus Hf, okay? That's what it is. So if we recall from our previous lectures in ITF, we know that the formula for enthalpy is equal to the internal energy plus the pressure times the specific volume, which has a unit of joules per kilogram. Okay. Now, the enthalpy of vaporization, the latent heat, like I said, is denoted by HFG. Okay. So when we want to vaporize a liquid, or we want to melt and vaporize melt solid water to liquid, vaporize it from liquid to gas, we will need to add heat, and that at the point where this happens, where these phase changes happen, we refer to that as the latent heat. So for the latent heat of vaporization, then this is presented as HFG. Okay. So for example, a rigid tank contains 50 kilograms of saturated liquid water at 90 degrees Celsius. Determine the pressure in the tank and the volume of the tank. First thing is a rigid tank. There is no inlet or outlet in the tank. So we will assume that the tank is filled up by this liquid water. So for us to determine the pressure of the system, we know the temperature of the system. So the pressure of the system will be the corresponding saturation pressure. All we need to do is what? We go to the steam table. So if we go to saturated water and steam, and we know the temperature is at 90 degrees Celsius. So remember, the unit here ran in bar for pressure. So if you go to 90 degrees Celsius, then the corresponding pressure, which is saturation pressure, will be 0.7011 bar. Okay. Remember the unit. Here is kilopascals. How do we convert bar to kilopascals? Most of you already know. You need to convert that to kilopascal. Okay, 100. I think 1 bar is equal to 100,000 pascal. Okay, so if you do the math and you convert using those figures there, then you convert this to kilopascal. Okay. Now it says the volume of the tank. So how do we calculate the volume of the tank? We know the mass of the liquid contained in the tank. So what about finding the specific volume? So we take the temperature reading of 90 degrees Celsius and we go back because it's liquid water. So we look for V of F, VF. So here we have Vg. So if we go to further properties of water and steam, so we have Vf, which is the specific volume of liquid water. So we go to 90 degrees Celsius. So 90 degrees Celsius and the corresponding specific volume is what? 0.1036 times 10 raised to the power minus 2 meter cube per kilogram. Okay, so if we plug that in here, it becomes 0.103 times 10 raised to the power minus 2 meter cube per kilogram. Okay, so for us to determine the volume of the tank, we know the mass of the liquid contained in the tank. So you just have to multiply it to cancel out the unit here. So 50 kilogram cancels the kilogram here, cancels out the kilogram. You're left with the meter cube, and this is the volume of the tank. So second example. So a mass of 200 grams of saturated liquid water is completely vaporized at a constant pressure at 100 kilopascal. Determine the volume change and the amount of energy added to the water. So if we know the mass of the liquid, first thing we do first is to convert this to kilogram. Okay. Then it says determine the volume change and the amount of energy added to the water. So this is a process of vaporizing liquid water to vapor. So there has to be at a point where there is a phase change. So we need to calculate the energy added to the water to vaporize it. So that's the latent heat of vaporization. So determine the volume change. What will be the change in volume from liquid to gas? So if we know the specific volume of the liquid water, because we have the constant pressure of kilopascal. Okay, so we convert this, okay, pressure to bar to find the corresponding specific volume of fluid. So we go to steam table. So we have the pressure in bar. So usually you have to do the conversion, knowing what the change is between how to change pascals to bar. Then when you do that, you get the reading of that pressure reading, you get the specific volume reading against that pressure calculation. Then that will be this. Then you do the same for the saturated vapor, which is Vg, and that will give you this value. Now, for us to find the total volume uh, of the total volume change, then it has to be the change in volume is equal to the mass, the total mass of the liquid that is being vaporized times the volume of the gas formed minus the volume of the liquid. So, and that will give us this. And the volume change is given as this value here. Okay. So, to calculate the enthalpy of vaporizing the liquid water, so we need to find the change in enthalpy at the 100 kilopascal pressure. So when we do that, uh, remember, convert this value to pascals, then you go to steam table. You are looking for enthalpy. So you are looking for the change in enthalpy, okay? So you're looking for the value in between here, okay? So once you have the conversion of the pressure, then you read against the middle value here. The middle value here is the latent heat of the pressure, okay? So when you do that, the unit here is in kilojoule per kilogram, and you are only required to calculate the energy added to the water. So we have the total amount of water. So the energy is now, change in energy is now equal to the mass, total mass of the liquid times the latent heat of vaporization, and that will give you the total energy in kilojoules, okay? So going from this point here, from liquid to gas phase, this is all we need to do. So to analyze a liquid vapor mixture, we need to know the proportions of the liquid and the vapor mixture in the phases in the mixture. So how the proportion tells us the quality of the mixture, and the quality, which is denoted by X, is equal to the mass of the vapor phase divided by the total mass, and the total mass is given as the mass of the vapor plus the mass of the liquid. Okay, so uh, but how do we why do we need the quality? Why do we need to know the quality of the system? So the quality of the system consisting of saturated liquid is 0, but the quality of the system consisting of saturated vapor is 1. So with this, we understand that a system that has a high amount of vapor is a high quality system compared to a system that has this system, because we is a mixture of vapor and liquid. So a system that has a high quantity of liquid is a low quality system. Okay. So during the vaporization process, only the amount of saturated liquid and saturated vapor changes, not their property. Okay. So the only thing that changes is the amount, the amount of liquid as the liquid is being vaporized, converting to gas. So meaning that initially it started as liquid. So but obviously as it exists in equilibrium, it's a liquid and vapor phase. But the vapor comes from liquid. So meaning that the more vapor is formed, then the less the liquid remaining in the system. So the amount of either the vapor or the liquid phase could change as a result of higher vaporization and or as a result of higher condensation. So the 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 amount will change, but the property that makes them up will not change, because there is the pressure is constant and there is a thermal equilibrium at that stage. So if you recall in the previous slide, it's a horizontal line. So that horizontal line says that the temperature remains constant while the pressure remains constant. And the pressure and the temperature, the properties of the materials within this the liquid or the vapor phase are dependent on the temperature and pressure. And if the temperature and pressure remains constant, then every other property will remain constant at this stage. Okay. So a saturated mixture can be treated as a combination of two subsystems, the saturated liquid and the saturated vapor. We imagine that the two phases are mixed well, forming a homogeneous mixture. The properties of the mixture is then the average property of the saturated liquid. So the how do you calculate the specific volume of this mixture? So the specific volume of this mixture is equivalent to the average volume of that's Vg, Vf for the combined. Okay, so the combined average, which is given as VAV. So the AV here means the average specific volume for the two. So that's what it is trying to explain. So since that has been established, then we need to find multiple ways to calculate for the quality of the system. Okay, the quality, like we've already seen in the previous slide, is given as x equal to the mass of the gas phase divided by the total mass. Now remember, in the introduction lecture, I've gone over how this is derived. So if you have more questions on this, you can ask me during the tutorial session because I will not repeat it. So what we are trying to say is that other properties at this stage, okay, remains constant. And since they remains constant, then we can also use it in place of the specific volume. So if the enthalpy is known, we can interchange it in place of the specific volume. Okay. So, and that will give us other formulas to calculate for the quality. So meaning that instead of using the relationship of the quality and the specific volume, we can also relate that to the enthalpy and the internal energy. Okay, because the property remains the same at this constant pressure and temperature. Okay, so example, a rigid tank contains 10 kilograms of water at 90 degrees Celsius. If 8 kilograms of water is in the liquid form and the rest is in the vapor form, determine the pressure in the tank and the volume of the tank. The pressure must be saturation pressure. So at 90 degrees Celsius, what is the corresponding uh, pressure? Okay, so if we go to the steam table as well, we find the corresponding pressure at 90 degrees Celsius, and make sure you convert to kilopascals. Then we do the same, we calculate for the specific volume of liquid water and specific volume of the vapor or steam in this case at 90 degrees Celsius, and that those numbers are given here. So it says, the first question says, um, determine the pressure in the tank and the volume of the tank. So we've already determined the pressure in the tank. So for the volume in the tank, it has to be the volume of both the liquid and the gas phase. And if the total volume will be given as the mass of the fluid that's opening up this volume here. So the mass of the fluid times the specific volume of the fluid in this case F, referring to liquid, plus the mass of the vapor times the specific volume of the vapor. And since we know all these value, which we found from the steam table, and the ones that are given, okay, then we can calculate the total volume of the tank with that, okay. Remember, it's a rigid tank. A rigid tank, there is no inlet or outlet. Everything is just a tank that contains materials in it. And you take assumption that the vapor phase will fill up the tank, even though the liquid phase will not fill up the tank. But the vapor, due to the properties of gas, as we've already explained, we make sure that the tank is filled. So that, with that said, the combination of the volume of both the liquid phase and the gas phase will tell us the volume of the tank. Okay. So superheated vapor section of the steam table. So this is characterized by lower pressures, higher temperatures, higher specific volumes, higher internal energies, and higher enthalpies. Okay. So comparing the uh, enthalpies and temperatures, these properties against the properties of saturated steam, then the superheated session will always present you with higher temperature, specific volume, internal energy, and enthalpies. So the fourth example here, to determine the temperature of water at a state of P equals 0.5 megapascals and uh, enthalpy of 2,890 kilojoules per kilogram. So first of all, we know the pressure here at 0.5 megapascals, okay? So we need to find the corresponding saturation enthalpy, okay, for water vapor. Now, you go to steam table, make sure you convert these megapascals to bar, then you look for the corresponding enthalpy for water, which is for water vapor in this case, which is Hg, and that gives us this. So the saturated vapor enthalpy is less than the enthalpy quoted, okay, for the pressure here. So this tells us that uh, because this enthalpy is greater than the saturation enthalpy of the vapor at 0.5 megapascals, then this tells us that this is a superheated steam, okay? And with that knowledge, we can go back to the table. So find where this 2890 kilojoule falls in this superheated steam. Here we go, superheated steam table. Okay, so you look for H. H represents the enthalpy of the vapor phase. So you look for where this 2890 falls. And from the table, it falls between 200 degrees Celsius and 250 degrees Celsius. So what do? We do a linear interpolation to identify the corresponding temperature. Okay, so this corresponding temperature is against 0.5 megapascals. Okay, so compressed water, compressed liquid. So for compressed liquid tables, they are not commonly available. So the key reason for this is the relative independence of compressed liquid properties from pressure. So the variation of properties of compressed liquid with pressure is very mild. So increasing the pressure 100 times often causes properties to change less than 1%. So in absence of the compressed liquid data, a general approximation is to treat compressed liquid as saturated liquid at the given temperature. Okay, and this is because the compressed liquid properties depend on temperature much more strongly than they do on pressure. So the compressed liquid character is characterized by this: higher pressure, then lower temperature, lower specific volume, lower internal energy, lower enthalpies. Okay, so unlike the superheated vapor, the compressed liquid properties are not much different from the saturated liquid vapor. So the final calculation example here. So determine the internal energy of compressed liquid water at 80 degrees Celsius and 5 megapascals using saturated liquid data. So from the saturated table at 80 degrees Celsius, what is internal energy? The internal energy is given as this. So you go to your steam table, then you find, remember, unit conversions. Okay, in this case, it's 80 degrees Celsius. So you can look for temperature at 80 degrees Celsius. You can do an interpolation here, okay? Or you better still, you can go to the saturated, you can go to saturated liquid table to get it, because as we've already said, we can use an approximation of, due to the change in pressure does not really affect much other properties. So we can take the reading from here as well. So if you go to temperature at 80 degrees C, then you read the corresponding internal energy UF. So we go to further properties of water. So we are looking for where is internal energy. If we scroll down, yeah, here we go, internal energy at 80 degrees Celsius. So this is 80.3 degrees Celsius. So you need to do an interpolation here, okay? So the number will fall between 332 and 336, okay? So between 332 and 336 for 80 degrees Celsius, and this is the value we arrive at, okay? So that will be it for this lecture. And please, if you have questions, bring it along to the tutorial session, and make sure you attempt to complete the tutorial from last week. So because this week I'll be asking you about them. Okay, see you guys in the tutorial session.